Welcome to Study Loop.
In this exercise, we have to consider a particle in a box that has walls at x equals 0, so this left wall here, and x equals L. This is the particle in a box we are used to. And now we have to consider a change in perspective. So basically, instead of putting the walls at x equals 0, we put them at x equals minus L over 2 and x equals plus L over 2. Remember that the solution for a particle in a box that has walls at 0 and L, as in the first figure, is psi equals a times sine of n pi over L times x. And in this exercise, we're going to have to consider that the possible solutions for a particle in a box that has walls at x minus L over 2 and L over 2 are a times sine of kx and a times cosine of kx. In question A, we're going to have to use sine of kx, so we're going to have to work with psi equals a times sine of kx, and we're going to have to apply the boundary conditions so that we can obtain the possible energy levels. So notice that according to the boundary conditions, the wave function at the walls must be equal to 0. Okay, so this means that a times sine of KL over 2 must be equal to 0. Okay, and also it means that minus a over times sine of KL over 2 must be equal to 0, which simply gets us to the previous equation. Okay, so this other equation doesn't add anything new. Now for sine of KL over 2 to be equal to 0, KL over 2 must be equal to a natural number n times pi. This means that K is equal to n pi times 2 divided by L. Okay, this is the value of K. Now remember that the energy of a free particle, the kinetic energy, is equal to h bar squared k squared divided by 2m. So in our case, this is h bar squared times k squared, which is 2n squared times pi squared divided by 2m L squared. So if I write h bar as h divided by 2 pi, we get h squared divided by 4 pi squared times 2n squared pi squared divided by 2ml squared. So I'm going to write the energies as h squared times 2n squared divided by 8ml squared. These are the energies. Okay. And we have to do the same thing now for the solution psi equals a times cosine of kx. So again, we have that a times the cosine of KL over 2 must be equal to 0. So I have that KL over 2 must be equal to 2n plus 1 over 2 times pi. Notice that the cosine is 0 when the value of x is equal to an odd number divided by 2, so it's 1 over 2, then 3 over 2, then 5 over 2, and so on. That's why I can write the values for KL over 2 to be equal, so that the cosine is equal to 0 as 2n plus 1 pi divided by 2. So K is equal to 2n plus 1 times pi divided by L. Again, the energies are h bar squared k squared over 2m. So this is h bar squared times k squared, which is 2n plus 1 squared pi squared divided by 2ml squared. So again, we get h squared times 2n plus 1 squared divided by 8ml squared. In exercise C, in question C, so first of all, here is the answer to question B. These are the allowed energy levels. In question C, we have to compare this with the result for the case when the walls are at 0 and L. In that case, we know that the energies are equal to n squared h squared divided by 8 ml. So let's compare with the two results we get here. So we have that for the sine solution, the values of the energy are 2n squared h squared divided by 8 ml squared, while for the cosine, the values are 2n plus 1 squared h squared divided by 8 ml squared. Okay, and notice that the values of the first set of energies are equivalent to the values of the previous set of energies, the one that I'm marking here in blue, as long as n is even n. While for the second set of energies, the value is correspondent to the previous values of energies for odd n. Okay, so in total, both sets of values of energy are consistent with the values we had before. Okay, and in question D, we have to answer which function that we had before. So we had two functions. We had psi is equal to a times the sine of kx, and psi equals a of cosine of kx, and we have to decide which one of them is odd and which one of them is even. Now remember that an odd function is such that f of minus x is equal to f of x, minus f of x, and then, so this is an odd function. And an even function is such that g of minus x is equal to g of x. So this is an even function. So remember that the sine of minus kx is equal to minus the sine of kx. So this means that the sine is an odd function, and hence the first wave function is an odd function. Now, the cosine of minus kx is the cosine of kx. So the second wave function is an even function. And this concludes our exercise.